show that reflections of domineering positions don't change their values. As an example, let's consider this eastern portion of a game we've previously encountered as the north. Let's reflect the game about a vertical axis. This yields another game, which we'll call the reflected northeast. If instead we rotate the northeast, we obtain its negative, which is minus northeast. If we add the northeast to its negative, we obtain a game of value 0, which the second player can win by matching. But minus NE can also be matched with reflected NE in the same way that it matched with NE. So reflected NE minus NE is also equal to 0. Adding NE to both sides of the equation yields the obvious conclusion that the value of reflected NE is equal to the value of NE. We'll next show a simple way that some big games can be decomposed into sums of smaller games. The reason for pursuing such a decomposition is that the smaller games might be much easier to analyze. Let's now consider this domineering position, which includes a protruding single square. If we block off the single square, the block can only hurt red. Blocking it is equivalent to separating it from the rest of the game, which is hidden under the cloud. Let's now consider another position, in which the position under the cloud was augmented by a sequence of 3 protruding squares. His move on the top row yields the cloud with a 1 square protrusion. His move on the bottom row yields only the cloud plus 0. Since we have seen that the position with a protrusion is at least as good for him as a position without it, it follows that Wright's move on the bottom row is bad. Blocking this bad move does not hurt red, because a competent red player would never need to play it. So whenever there is a protrusion of length 3, we can cut it apart from its more extreme 2 squares without changing the value. Recall our position S and its negative minus S. These are taken from our previous game. Let's now denote the restricted version of S by the letter T. Since the restriction applies only to red, it might conceivably be an advantage for blue. So perhaps T is greater than S? Or is the blocked move a bad move for red, which red would never need to play anyway, in which case T equals S? When playing minus S plus T, can blue going first win? Most initial blue moves in minus S plus T can be matched by the appropriate red response. So if blue intends to win, he'll eventually need to play this move in minus S, moving it to minus S prime. But in this case, red has another effective response. Now as shown by the triple dots, this same red response would be effective against blue's move, even if various matching pairs of moves had been played earlier. Hence, despite the nominal disadvantage of having one of his possible moves blocked, red going second can still win in minus S plus T. The value of the game is not changed by the blockade, because the red move it prohibits is a bad move which red never needs or wants to play. Instead of viewing the heavy line as a blockade, we might also view it as a value-preserving decomposition. It allows us to cut the South into the sum of 2 simpler games. Every proposed blockade must be examined with care. Here is one that changes its value. If we accept the blockade, the blocked value is 1 plus minus 1 equals 0. But we know that without the blockade, the value is minus a half. So this blockade does really hurt, right? Because it increases the value from minus a half to 0. Many domineering positions can be decomposed in ways that preserve their values, although each proposed decomposition needs to be carefully checked. We'll now show how a sequence of such decompositions can simplify a position enough for the postmortem kibitzers to analyze it correctly and relatively quickly. Let's now continue our analysis of the ending of the first game we showed in this video. Here was the position after move 16. As usual, we'll white out the played squares and eliminate the 0 square. There are a few integers in the northeast which cancel each other out, so we can eliminate them. We'll next propose to blockade a blue move at the bottom of the northwest. It's not hard to confirm that this is a legitimate value-preserving decomposition. The decomposition splits off a region of value +1 with which we can cancel out a -1 in the southwest. We then find another legitimate decomposition at the bottom of the shortened northwest. And this peels off another +1 with which we can cancel out a -1 near the center of the board. We next propose a vertical blockade against red in the remaining northwest. After verifying that this too is a legitimate blockade, we can split the northwest into two simpler regions and consider another blockade in the south. After checking that this blockade is also legitimate, we can separate it off. So we've decomposed the full board position after move 16 into the sum of 4 much smaller positions.